And with this lesson, we are going to discuss prime and composite numbers. Our objective is fairly straightforward. We want to create a factor tree and use the factor tree as a tool to figure out what the prime factorization of a number is. Now, before we go on, there are a couple of pre-existing skills that we expect you to already have. For instance, can you split numbers up into factors? For an example, can you tell me two numbers that are going to multiply to 30? That's a skill that we are going to use. And if you want to use a multiplication chart to help you out with that, go ahead.
10 and 3.
Yes, one way to do that is 10 and 3. And with our previous lesson, we were going over divisibility rules, saying, does 2 divide into the number? Does 5 divide into the number? Using the divisibility rule is only there to help you split numbers into factors. Now, to continue, we're going to start off with this piece of vocabulary. A prime number has only 2 factors, 1 and the number itself. The first 6 prime numbers, and you may want to write this at the top of your sheet as a reference if you don't already have them memorized. The first 6 prime numbers are 2, 3, 5, 7, 11, and 13. Now what that means for us, if we try to split up 5 as a prime number, the only way you can multiply and get 5 with whole numbers is 1 times 5. You can't split it up with 2 times 3, it'd be 6. You can't split it up as 4 times 2, which would be 8. Same thing with 13. You can't split them up. The only way to do it is 1 times 13. 2 will not divide into it evenly. 3 won't. Nothing does except 1 and the number itself. If you have a number that can be split up, like 24, it's called a composite number. And our goal then for this video is to see how you split numbers up until you get only these prime number chunks. So how do you split 24 up until you get nothing except the numbers that are like this? How do we do that? Well, to start off with, we're going to do the prime factorization of 30. And we're going to use a factor tree as a tool. Tell me 2 numbers that multiply to 30. 10 and 3 we had mentioned earlier. Well, in our list of prime numbers, the first 6 of them we said were here. 3 is on that list. We can't split that up anymore, so that one stops. 10 is not a prime number. You can split up 10 again. 5 multiplied by 2. And then we'll notice 5 is on our list of prime numbers. 2 is on our list of prime numbers. Anything that's on our list of primes can't be split up, and so we stop. All these ones that I've circled then, we just need to multiply them out. 5 times 2 times 3. This is our prime factorization. Factorization just means it's a bunch of stuff that multiplies and is the same. 10 times 3 is a factorization of 30, because 10 times 3 is the same as 30. But we want to have it so that there are only prime numbers being multiplied. Down here in the box, that's what we've got. What about the prime factorization of 42? We need some numbers that will multiply to 42. Can you think of any? The first ones I was told were 7 and 6. While that was coming along, somebody else said, well, 2 is going to work, and you're right. 2 times what? Whether you're using a multiplication chart or you do the long division, you can split it up this way. Both of these are valid ways to go. We could do it either way. It doesn't matter how we start. And for this particular problem, I actually want to go through and do it 2 different ways so that we can see that it doesn't matter how we begin. And I'll bring back our list of prime numbers, our first 6. We'll notice 7 is a prime number. 6 isn't. That one we can split up as 2 times 3. And so we get our prime factorization, 7, 2, and 3. That is correct. We'd be done. Now we'll also continue. 2 is a prime number. 21 isn't. How could we split up 21? That's 3 times 7. 3 and 7 are primes. And so when we put them down, we have 2 times 3 times 7. You notice that the orders are not the same? It doesn't matter. As long as we have the numbers, we have a prime factorization. Both of them are correct prime factorizations. There's nothing wrong with either one of them. However, if it's more common, just because it's easier for people to understand, we prefer to have them written like this, where we put the numbers from smallest to largest. Putting them in order from smallest to largest just makes it easier for people to understand usually. So even if you get the answer here, 7 times 2 times 3, we would prefer if you rearrange it, taking the 2, followed by 3, followed by 7, and get them in order. It just makes it easier for people to make sure that you're correct. Now let's get this one, the prime factorization of 91. Okay, so what are some numbers that will multiply to 91? You kind of have to keep in mind, the prime numbers we're checking, 2, 3, 5, 7, 11, and 13. Do any of these work? A lot of times people won't recognize it, which is why the multiplication chart is helpful, and I've seen some students already start checking them, and on their multiplication chart they saw that 91 is actually equal to 7 times 13. And so, since those are both prime numbers, our prime factorization is 7 times 13. We wanted to go over this example just so that you would be aware that just because a number looks kind of weird, that doesn't instantly guarantee that it's a prime number. You do need to go through and check. And this set of 6, as the smallest prime numbers, they're the ones that get used most frequently. You should expect to check all of them. What about here? 89. What is the prime factorization of 89? So when we start checking pieces, because it ends in a 9, 2 is not going to work. Our divisibility rule would fail. To check the 3, 8 plus 9 is 17. 3 does not divide into 17. And so the divisibility rule for 3 fails. In order for 5 to work, you have to go, the number has to end in 0 and 5. That fails. In order for 7 to work, well, we were just looking at the ones for 7. We saw that 7 times 13 is 91. Just looking at the multiplication chart, we can rule out both 7 and 13. And with 11, 11 times 8 will equal 88, so 11 gets skipped on the multiplication chart. Basically, we start running through all of our prime numbers, and we could keep going with the next prime numbers are 17, followed by 19, followed by 23, followed by 29, followed by 31. And we could keep going and checking prime number after prime number after prime number, but ultimately, none of those are going to work. And none of them work because 89 is a prime number. The only way to split up 89 is with 1 times 89. But since since 1 is not a prime number, we can't use that in a prime factorization. That is our prime factorization. It's the number itself. It can't be split up, so we're just going to call it prime and then we're done with it. Now we'd like to be able to see how does this prime factorization stuff actually get used, outside the classroom. Well, one of the simplest ones is a paycheck. You get paid every 2 weeks, and you have an annual salary of $40,000, is it possible for you to get the exact same amount on every single paycheck? Now, where this starts coming into play, if you get paid every 2 weeks, how many paychecks do you get per year? Well, there are 52 weeks in a year. And so if you split up all the 52 weeks amongst two, getting a paycheck every 2 weeks, that'll tell you that you get 26 checks per year. By the way, that's exactly how my salary is set up. I get paid every 2 weeks, so I get 26 paychecks per year.
Is it 40,000?
All right, so basically what we're wondering then, if you try to take the $40,000 salary and split it up amongst 26 paychecks, is it going to divide out evenly? Yes or no?
Yes.
Well, we did not have a divisibility rule for 26. And we did discuss that since 26 is equal to 2 times 13, we could use the divisibility rule for 2 and use the divisibility rule for 13, and that would work. Except we don't have a divisibility rule for 13, so it won't. Basically, we have two different strategies we could do to answer the question. One of them is to actually do the long division. Divide it out. 26,000 going into 40,000, does it come out even? Just do the division and see if it works. A lot of students are going to prefer that method, especially if you've got a calculator handy. It's very quick just to hit it into the calculator, 40,000 divided by 26, enter, and then look. That's probably the fastest and the easiest way. But I would like to note that we can do it based on a factor tree. A factor tree gives us 2 times 13 for 26. If we get both the 2 and the 13, if both of them show up in our factor tree for 40,000, that will tell us, yes, it is possible. But if one of them does not show up, the whole thing's going to fall apart. And it won't work. We can't get even paychecks unless both primes are there. So we need a pair of numbers that are going to multiply to 40,000. How about 40 times 1,000? Then that would give us 40 can be 4 times 10. 1,000 can be 10 times 100. 4 is equal to 2 times 2. We've got prime numbers. 10 is equal to 2 times 5. Got those. 10 is equal to 2 times 5. 100 is 10 times 10, which gives us 2 times 5. 2 times 5. Did we get both of them? We did get the 2. We got the 2 in several places, but we did not get the 13. And because the 13 is missing, that lets us know it is not possible for you to get the exact same paycheck every single time. There's going to have to be some kind of a rounding error. Sometimes maybe you'll get 5 cents, and other times you'll get 3 cents on the paper check, on your check. There has to be some kind of a rounding to make it work.
So do we have to do it like that? Or?
And that finishes us off. We've seen how to create a factor tree, how to list out the prime factorization, and also one example for how you could use prime factorization to actually figure stuff out in your day-to-day life.